Welcome back, physics fans, and here we go on to springs. We're going to talk about elastic forces. It's also known as Hooke's law. Hooke's law. Okay? An elastic force acts to return a spring to its natural length. So if we have a spring, here's my beautiful diagram of a spring. If it's at its rest length, that's its natural length. And when you start pulling on the spring, it requires a force. And when you let go, it goes back to its rest length. And when you apply a force, it stretches. The distance there, it stretches. An ideal spring is taken to be massless, frictionless, unbreakable, and infinitely stretchable, but there's no such thing. But we're just talking about ideal springs here. We're just learning about the concept. Such springs exert forces that push when you are contracted or pull. So if we pull it, it wants to pull back. If we end up squishing the spring and compressing it, it will want to push back. As we push it together, it will want to expand. And it actually follows a particular law, and it is in proportional to the displacement. So if you stretch it twice the distance from its rest length, it'll require twice the force. And this is a linear relationship described by, well, guess who? Robert Hooke, named after him in 1679. Okay, so delta x is how much it is pulled away from its ideal length. And the force that we pull on it is called the elastic force. And it's equal to negative kx. Now, the negative means it wants to pull back. As you pull this way, the elastic force pulls back. Okay, so you pull this way and the elastic force pulls back, and that's why it's negative. And each K is called a spring constant, and it has to do with that particular spring that you're pulling on, and it's basically how hard it is to pull it. So if you try to stretch and compress, we get this formula. The elastic force is equal to Kx. If you want, you could put a negative in there. We just know what direction the elastic force is. And X is how much in meters the length has changed. And the change in the length could be a compression or an extension. So it depends if you're compressing it. So the spring constant of a rubber band, about 700 newtons per meter. But you know, the steel in a building is about 21 million newtons per meter. So it does compress. The steel structure does, gets thinner, or squashed down, but not very much. And that's probably also why we make skyscrapers out of steel and not rubber. So let's just get using this simple equation. A steel spring has a spring constant of 40 newtons. Okay, that's just made up, 40 newtons per meter. How much force would it take it to stretch it 10 centimeters? So the pull force would equal the elastic force, and it's going to be the opposite direction, but that's okay. And it's Kx. So the K is 40 newtons per meter, and X is 0.1 meters. Okay, so there's our trickiness. Most springs we don't stretch meters, we stretch centimeters and millimeters. So you have to watch out on those conversions. And this is just going to, the meters will cancel out, and you can see that it's going to be in newtons, and that's going to be 4 newtons. A garage door has a spring constant of 600 newtons per meter. How much will it stretch if a 150 newton force is applied to it? So we have the elastic force is equal to Kx, and 150 newton force is applied to it, and K is 600. We have to try to solve for X. X is going to be 150 newtons, and it's 600 newtons per meter. and this is going to equal 0.25 meters. Okay, number 3. What is the spring constant of a car spring if 2,500 Newton force is compressing it from a length of 50 to a length of 40? So the spring is originally 50 and now it's 40. So you've compressed it how much? You've pushed on it with 2,500 newtons and it compressed it 10 centimeters. It went from 50 to 40. So F elastic is Kx, and the force is 2,500 newtons. And the K is what we're trying to determine. So maybe I'll put that in black so you can see it. And how much we've compressed it is 0.1 meters. So K is going to equal 2,500 newtons divided by 0.1 meters. The units are newtons per meter, which it should be because that's what we're told. Spring constants in newtons per meter. And this is going to be 25,000 newtons per meter. Okay, and that's basics of Hooke's law. Now let's see if we can apply it in a little bit bigger situation. Let's try number 31. A 5 kilogram mass is suspended by a spring. So we have a spring. And that spring is stretched 2 centimeters. So it has pulled out the distance as 2 centimeters. What's the spring constant? Okay, well, free body diagram would be good. We have an elastic force that's pulling it up, and we have a gravitational force pulling it down. And it's suspended, so I'm going to assume that that acceleration is 0. It's not accelerating up or down. So the sum of the forces is equal to F net equals ma. There's not one that's winning, so I'll just go elastic force is winning minus the force of gravity is equal to ma, but a is 0, so that means the elastic force minus the force of gravity is equal to 0. That means the elastic force is equal to force of gravity. Pull that on over, and we get Kx is equal to mg. And the K is the spring constant, so that's just going to be mg all over x. So K is going to equal 5 kilograms times 9.8 newtons per kilogram all over x, which is 0.02 meters. Let's just see if we're doing this right. This is pretty decent. We'll just take a look at that the kilograms cancels the kilograms there, and we're going to end up newtons per meter, and that's what we want. And Mr. Calculator, well, let's go 5 times 9.849 divided by 0.02, and we get a spring constant of 2,450 newtons per meter. Okay, so that is how we do spring constants. Thanks, subscribe, smash that like button, and leave your comments down below. Thank you.